So far, we introduced this thing, f of x modulo p. This is a ring of polynomials, f is a field, p is a polynomial, and we introduced this set as the set of equivalence classes, which is parallel to Z mod n. Now we will, as we did in the case of Z mod n, introduce operations on this set. These are operations of addition and multiplication. So f is a field, f of x is the ring of polynomials with coefficients in the field f. P is a polynomial with coefficients in the field f. Where the operations are introduced exactly as in the case of integers of residue classes modulo an integer. Namely, we write that f plus g equivalence class modulo the congruence relation which contains f. F is a representative of its class. Will be defined as the equivalence class of the sum of polynomials f and g. If these were integers modulo n, the formula looks exactly the same, the definition looks exactly the same. Same thing about multiplication. Product of two classes is the class which contains the product of polynomials f and g. We immediately got to check that these definitions are that these operations are well defined. Namely, if I choose from this same class another representative, from this same class another representative, the classes stay the same with some two different representatives, it should be still the sum a representative of the same class. Otherwise, the formula makes little to no sense. As soon as, but it is easy to check that the operations are well defined and the procedure is exactly the same as we did for integers. With these operations, the set of equivalence classes becomes a ring. This is also a claim to check that after all requirements, all axioms of a ring are satisfied. Altogether, summing up, this is what Theorem 5.7 in the book claims. Let P in be a non-constant polynomial. The set with the operations defined above I mean by these formulas is a commutative ring with identity and the role of identity 1 in this ring is played by, not surprisingly, the class of 1 in the field F. Furthermore, f of x modulo p contains a subring which is isomorphic to F. I will not present the proof. It is easy and described in the book, but the last sentence here, starting with furthermore, requires some comments. This is something new. The rest is exactly in the case of exactly parallel to Z mod n. So everything is the same, starting with n, an integer. Everything is the same as there, so nothing new besides the new last sentence. So let me comment about this last sentence. So comments on furthermore. So as a set, this thing looks like, and we know that I just copy from here. This is how f of x mod p looks as a set. I will copy it here. This is the class of 0 and the classes of non-zero polynomials such that the degrees are smaller than the degree of a polynomial p. In particular, we have a subset which consists of the class of 0. I still put it here. 0 has no degree, therefore the annoying necessity to every time write it separately, because all these polynomials must be not 0 to have a degree. 0 does not. And among polynomials who have degree smaller than degree p, we started with a non-constant polynomial p. P is non-constant, so p has a degree which is positive. So this is a positive integer. Degree p is a positive integer. Thus, all polynomials of degree 0 are here. There are possibly some polynomials of degree higher than 0 if degree p is a big positive integer. There are quite a few polynomials with smaller degrees. However, among them definitely are degree 0 polynomials. So I will write R who are degree 0 polynomial. If degree 0, if degree of polynomial is 0, then, or put it even differently, I don't want to write too much, so degree of a polynomial is 0 if and only if the polynomial is a constant. An element of f, of course, different from 0. So these are just constants. So what do we have after all? We have 0 and all non-zero constants. which is same thing as R0. 0 is an element of F, and all other elements of F which are not 0. So this is what we wrote here. R in brackets for all R in F. Let us say that this set is F star. Sorry, it is not equality. Of course, it is this set of all polynomials contains this as a subset polynomials of degree 0. Maybe only polynomials of degree 0, maybe something else, but this set contains a subset F star of elements of F in brackets. The operations are defined here in a way such that they satisfy, they are the same operations as operations in F. So the operations are defined such that the operations on the set are defined in a way such that F star is a subring of this ring, and the operations on F star are the same as on F. If these by an accident are elements of F, we still sum them together. These by an accident are two elements of the field, we multiply them together. So this is a subring with same operations as on F. So F star becomes a subring, and this subring is isomorphic to F. The isomorphism looks as follows, where make a map from F to F star, take an element A and map it to A in brackets. Everything is defined in a way such that this is an isomorphism. That is basically a proof or explanation of this new property, which this is a new phenomena which we did not observe for integers. Let me also do some remarks about the new ring which we have produced in this way. If what happens in a special case, so if we execute the same construction, but drop it non-constant polynomial. If P is a constant polynomial, that means that P is an element of F, and assume that still P is not 0. The construction goes through easily and produces equivalence classes. However, plural is probably not what one should say here, namely, remarks. There will be two remarks. Namely, we have if then we produce one equivalence class. That is because every two polynomials are congruent modulo constant polynomial non-zero. This is a unit. And f of x. Well, that is very easy to check this. Just take the definition. What does it mean for two polynomials to be congruent modulo another polynomial? Check, or let me do it for you. Indeed, take any two polynomials. What does it mean to be congruent? Means U divides their difference. Which means their difference can be written as U times some other polynomial h. Indeed, this is a unit, so it's invertible element. There exists U inverse. Multiply everything by U inverse. To get h is U inverse times f minus g. We always can do that. So every tuple, thus U inverse is an element of f of x. This is a unit in the ring. It's actually an element of f, therefore an element of f of x. So thus, for every two polynomials, we take this h, and we got this equality, which means that the unit divides the difference. So every two polynomials are equivalent, means every two polynomials are congruent, means every two polynomials belong to the same class. All polynomials belong to the same class. We have exactly one equivalence class. Alright, now we can introduce the operations and you can check it, but the right guess is correct. What you produce is the ring out of one element. There is only one element, one ring out of one element. This is zero ring. Thus, one has to check the operations. Oh. That nothing happens, we again produce a ring. And this is this, I mean, let me write it, f of x mod, let me write u for unit, or p, I already have p. In this case, is a ring out of one element, one equivalence class, one element, and this is zero ring. Zero ring. So everything goes through, and we produce a zero ring here. The last clause of our theorem, furthermore, the new one, is not true. Zero ring does not contain a subring isomorphic to the field. The rest is absolutely good. In this same way, you can take n to be 1 and see what happens here. You produce a zero ring as z mod 1. Alright, but then, this was the first remark, and the second natural question would be, what happens if we use this condition? If p equals 0f. Of course, we cannot speak about remainders from division. There is no division by 0. But we still can speak about congruences in a sense, meaning, so we cannot say okay, let me see. We cannot say that difference is divisible by 0. But we can say that difference is 0. So for divisibility, difference is divisible by u means difference is equal to u times something. We can similarly say f is congruent to g mod 0 means f minus g equals, as here, something times polynomial 0 times h. H is again a polynomial. I copy from here. H is again a polynomial, but that does not matter. Times 0, it is 0. So, means, in this case, f is congruent to 0 is equivalent to saying f is equal to 0. F is congruent to g mod 0 is equivalent to saying f is equal to g. Meaning, we have as many congruence classes, equivalence classes, as elements in f of x. So this equivalence relation means that the two are equivalent if and only if they are equal. So in this case, how did I write it here? Then all every element in f of x belongs to its own equivalence class. We have as many equivalence classes as we have elements in the ring. We can say then that thus we did nothing. It is the same set as it was. Zero f is the same as 0 f of x is same f of x. Every element forms its own equivalence class as sets, and obviously as rings. They are isomorphic if you want. So, although we cannot divide by 0, we still can take 0 as this polynomial. We just don't speak about divisibility, but write that one about this one. This one is impossible. 0 divides something makes little sense. But write it this way, and we got it. F minus g is 0 times a polynomial, which is anyway 0, means f is equal to g, means every equivalence class contains exactly one element. Means with this if we start with zero polynomial, we get back the ring as it was. We could do the same with integers. No harm. Gain, we simply get the ring of integers back. So in this case, everything works, including the furthermore statement of the theorem. So indeed, if this is 0, this is just f of x as it was, and it indeed contains a subring isomorphic to f. All elements of f, all constants, form, 0 included, form this subring. It is f itself, isomorphic to itself. In chapter 2, we described units in Zn. So recall, units in Z mod n. This is the set of classes such that the greatest common divisor of A and N is 1. We can do the roughly the same proof, a similar description for our new things, for the f of x modulo polynomial. Namely, the units in f of x modulo a polynomial, p non-constant polynomial. Here, and what we get, the classes such that the greatest common divisor of f and p is 1 now in the field. As I said, the proof is roughly the same as in the case of integers, and I skip it. Instead, I want to return back and to speak a little bit about this one. So I want to again speak about this isomorphic copy. So this is one more small remark. About this last sentence. So the ring contains a field as a subring. So all elements, all non-zero constants are among units. So here, there's units in this field, so any non-zero constant is here. Their greatest common divisor over non-zero constant with non-constant polynomial is definitely 1. There are no common divisors except units, well, for a constant, a non-zero constant. So non-zero constants, so remark, all non-zero constants say U in the field inside F of are among the units in general. In a ring, the sum of two units is either 0 or something, maybe unit, maybe not. In this case, sum of two units may be 0 or must be again a unit. This is a field. So in particular, the sum of two such units is again a unit. As F is a field, is again a unit if non-zero. Because F is a field. This does not happen frequently in a ring. For example, it is not common that the sum of two units is a unit again. It may happen, but not that common. Here there are lots of units which satisfy that. Say, in contrast, in Z, 1 is a unit, 1, number 1 is a unit, while one plus 1 is 2 is not a unit. So be careful, please. Have in mind, in general, in a ring, this is not the case. Units, or many units, may not may not constitute a subring. In this case, not all units constitute a subring. If it is a polynomial, maybe your sum of two polynomials which both are relatively prime to p may be divisible by p. So it is not necessarily you are there, but there is a whole subring of units. Here you don't have that. So in arbitrary ring, when you sum two units, chances are you get something which is not a unit. Although sometimes it is. All right. There is a reformulation of this furthermore statement, which is of interest and which we will address in the next segment. Thank you for listening.